Morning, everyone. This is Sajin Biske from SND College of Engineering and Research Center, Department of Electrical Engineering. In the previous lecture, we discussed some part related to stability of a control system and root locus. Now, we are studying the root locus for the second order system. What is exactly the second order system? So there are some basic general rules for constructing the root locus. The root locus is asymmetrical about the axis and the roots of the characteristics equation are either real or complex conjugate or combination of both. Therefore, their locus must be symmetrical about the real axis. As the value of k increases from 0 to infinity, each branch of the root locus originates from an open loop pole n numbers with k is equals to 0 and terminates either on an open loop 0, that is m numbers, with k equals to infinity. Along the asymptotes or on infinity, 0 at infinity. The number of branches terminating on infinity is equals to n minus m. Third one is determine the root locus of the real axis. Root loci on the real axis are determined by open loop poles and zeros lying on it. In constructing the root locus on the real axis, choose a test point on it. If the total number of real poles and real zeros on the right of this point is odd, then the point lies on the root locus. The complex conjugate poles and zeros of the open loop transfer function have no effect on the location of the root locus on the real axis. Next, determine the asymptotes of the root loci, and the root loci for very large value of s must be asymptotic to straight line whose angles are given by the angle asymptote phi a is equals to plus minus 180 in bracket 2q plus 1 upon n minus m, where this q is equals to 0, 1, 2 and so on, and n minus m minus 1. All the asymptotes intersects on the real axis and it is decided by sigma a and is given by sigma is equals to sum of poles minus sum of zeros upon n minus m. Now find the breakaway and break-in points. The breakaway and break-in points either lie on the real axis or occurs in the complex conjugate points. On the real axis, the breakaway point exists in between two adjacent poles and breaking point exists between two adjacent zeros. To calculate this polynomial, DDS of k means derivative of k must be equals to 0 and must be solved. The resulting roots are the breakaway or break-in point, and the characteristic equation is shown in the above equation and can be rearranged by b of s plus k into a of s is equals to 0, where b of s is equals to s plus p1 and s plus p2 and s plus pn, and a of s is equals to k into s plus z1 into s plus z2 into s plus zm. The breakaway and break-in points are generally given by derivative of k is equals to dA into mod of b minus a and derivative of b is equals to 0. We should note that the breakaway point and break-in point must be the roots, but not all roots are breakaway and break-in point. If the root is not on the root locus portion of a real axis, then this root neither correspond to breakaway or break-in point. If the roots are complex conjugate pair or ascertain that they lies on the root loci, check the corresponding value of k. If k is positive, then root locus is a breakaway or breaking point. Determine the angle of departure of the root locus from a complex pole. And angle of departure from a complex pole P should be equals to 180 degrees. Determine the angle of arrival of the root locus at a complex 0. Now we should have to find the points where the root loci may cross the imaginary axis. The point where the root loci intersect the j omega axis can be found by the use of root stability criteria or letting s is equals to j omega in the characteristics equation, equating both the real part and imaginary part to 0 and solving for omega and k. The values of omega thus found gives the frequency at which the root loci cross the imaginary axis. The corresponding k value is the gain at each crossing frequency. Now, the value of k corresponds to any point S on a root locus can be obtained by using a magnitude condition, or k is equals to one equation is there in numerator, product of the length between the points to pole, and in denominator the product of the length between points to 0. Now, phase margin and gauge margin of this root locus is given as, first we have to determine the gain margin. So what is gain margin? So it is the factor by which design value of the gain can be multiplied before the closed loop system and becomes unstable. Here the gain margin formula we can find out by in numerator the value of k at imaginary crossover upon the design value of the k. Now what is phase margin? Find the point j omega 1 on the imaginary axis for which g of j omega into h of j omega is equals to 1 for the design value of k, and this phase margin is given as phi is equals to 180 plus argument of j omega 1 into g of j omega 1 into h of j omega 1. So let us take one example. Sketch a root locus of a unity negative feedback system whose forward path transfer function is g of s upon g of s is equals to k upon s. Number one, root locus is symmetrical about the real axis. Second, there are no open loop pole, that is m is equals to 0. So the open loop pole is at s is equals to 0. Here n is equals to 1, and one branch of the root locus start from the open loop pole when k is equals to 0 and goes to infinity asymptotically when k tends to infinity. Next point, the root locus lies on the entire negative real axis as there is one pole towards the right of any point on the negative real axis. The asymptote angle is phi a is equals to plus minus 180 in bracket 2q plus 1 upon n minus m, where q is equals to n minus m minus 1, which is equals to 0. And angle of asymptote is phi a is equals to plus minus 180 degree. The root locus does not match the branch, hence there is no need to calculate the breakpoint. The root locus depends on the angle of minus 180 degree from the open loop pole at s is equals to 0. The root locus does not cross the imaginary axis, and hence there is no imaginary axis crossover. The root locus plot is basically shown, and it is generally a straight line. So the system is stable for all the values of k greater than 0. The system is overdamped. Thank you.